Hello everyone, I am trying to figure out how to get on. Okay, now I'm gonna do my key for fall 2023 exam for you guys who wanted a review of the key. And first question is, which of the following is not a nucleophile? And so again, I frequently start with something that should be a very straightforward question to gently ease you guys into the exam. So not a nucleophile, meaning it does not have electrons to share. Water, the lone pairs on the oxygen can share the electrons. Anything with a negative charge, nucleophile. Amines have lone pairs. Positive charge, clearly not an electrophile. All right. When we're looking, make sure you read through the whole question. A lot of times there'll be clues in the question. Here, they've already told you that it started out as an antiamerically pure S2-bromobutane. We told you it was an SN2 reaction with CH3O. So we're not even asking you, is it substitution or elimination, or is it SN1, SN2? We've told you it's SN2. Here is your nucleophile. They've drawn the product. All they want to know is what is the configuration. Since it is SN2, it has to fully invert stereochemistry. So if it started off as S, it has to go to R. So it would be the R only enantiomer. Which of the following alkyl halides reacts the fastest? Again, SN2. To determine speed on SN2, that's governed by steric hindrance. The less sterically hindrant, less hindrance. Oh, I don't want that either. Stop. Okay. Less hindrance, more stable. So that has to be the chloromethane, because all chloromethane has on it are other hydrogens. Each of these others have at least another carbon. So that will be the fastest. The 1-chlorobutane would be the second fastest. 2-chlorobutane would be slow but would go. And the 2-chloro-2-methyl propane would not go at all. Now, if we talk about SN1, we're talking about carbocation, and which has the most stable carbocation. And that is the most substituted. So the slowest at SN2 will be the fastest at SN1. Then they're asking about the rate law for SN1. And all they're asking, they don't even ask you for the number of the rate law. So read what you're given. And all they're asking is, what is factored into the rate law? It's a fancy way of asking that question. Here, rate laws, again, if we remember from Chem 2, we don't add. So we can immediately take those out. And if we remember SN1, the rate is determined by how quickly I can form that carbocation, which is solely dependent on our alkyl halide, and it's called an SN1 because it is a unimolecular kinetics. Based off of 5, if you look at 6, which of the following factors has no effect on the rate law? The leaving group always has an effect, because you can't do the reaction if your leaving group won't leave, right? That's why we don't use alcohols. The value of the rate constant, that doesn't even make sense. The nature of the alkyl halide, that, again, concentration of alkyl halide, if we got the question above correct, that we know is incorrect. Concentration of the nucleophile, remember, this is SN1, so how much nucleophile I have is not relevant. All right. This we went through. This was one of your quiz questions from this semester. If we look through, we can see this is Markovnikov, this is Markovnikov, this is Markovnikov, and this, we could do a carbocat rearrangement. So all of them will do that. Okay, which of the set of arrows is correct as drawn? They're not asking you for what reaction. They're asking you for which of these is correct based on the arrows. It could also be, what do the arrows depict? So if I look, I can immediately cancel out that. I can immediately, that's some weird arrow. Same thing here. That leaves me with A, and A looks correct. Those are the arrows for an SN2 mechanism. Which converts 2-butene to cis. So I'm looking for something that goes cis. I know this goes, A goes all the way to an alkane. B goes to a trans. C I've never seen before. And D also goes trans. My answer is E. This again, the question from one of our quizzes. We need to make sure when we're looking at the enol it came from, there has to be a double bond on the carbon that had the carbonyl. And the double bond has to be attached to the carbon that has the OH. Here, if you notice, I have no double bond, so I can't do that. Here, this double bond is not connected to the same carbon that the OH is on. Same here. Same here. My answer is A. Now I'm going to take a few moments and hopefully be able to draw on here the mechanism. So again, this is the type of thing you'll be expected to draw. Boom, boom, boom. Whoops. Let's undo that. Boom, boom, boom. Erase. Erase that. Now all I'm going to do is 1, 2, 3. And then we have this double bond, OH. If it's under H+, so I'm going to do H+ / H2O. We protonate. Protonate. And with that I mean the double bond protonates. And you have here a plus charge, plus. Then you do resonance. This is where a lot of you guys struggled on your Alex homework. They wanted the resonance arrows. Here's my OH. So when I do my resonance, I just show the arrow like there. And notice I'm showing each step. I am not skipping a step. I am not trying to do 500 things in one step. And then I deprotonate and regenerate my catalyst. Boom. Then this goes here. Yeah? So you show each step. I know this is not super neat because I'm on my iPad and I'm not the world's neatest on my iPad. Next, if you want to do this under basic conditions, it's the opposite way. First you deprotonate. And notice under basic conditions, I'm not going to have a plus, I'm going to have a minus. Just like under acidic conditions, I won't have a minus, I will have a plus. So now here's my deprotonated product, O minus. Here's my double bond, boom. Here's my resonance arrow, because now I'm going to go boom to here. And undo that. and go, oops, double bond here, yep, double bond here, dot, dot, minus. This is now, I'm going to protonate and regenerate my base catalyst. And now I have my product. You do whichever acid or base you want. Okay. Next question, the short answer, pick one. So the main reason, and I'm just going to go through this quickly, if we look at phenol, phenol, that's the more stable form of phenol, whereas this would technically be the ketone. For most of them, we get the ketone. For phenol, it mostly stays as the enol. Because if you look, this whole piece is aromatic. There's resonance you can do throughout. Once I get to my ketone, I don't have resonance I can do throughout. I've broken up by having this be sp3. Next question, elimination. So if I'm looking at an alcohol and it's under H3O, and keep in mind, you only needed to pick one. H3O plus and heat, I will get an alkene. If I do this with a base, OH minus, and heat, nothing's going to happen. And that's because I need this H3O plus. This is a bad leaving group. So it needs to be protonated. And that's why I need acidic conditions. I cannot protonate under basic conditions. Okay. Now I'm just going to go through and I'm going to write out the products here. Again, if I don't ask you to do the mechanism, you do not have to do the mechanisms. Here, I gave full credit if you did this with, whoops, this thing. Ugh, okay, I got to figure out a better way to be on this. Boom, boom, boom. There you go. Okay. I gave full credit if you did the methyl shift. 1, 2, 3, 4. 1, 2, 3, 4. I keep one here. And then I have this and a chlorine. Yeah? And it's achiral. If I did HBrOr, 4, 1, 2, Br, boom, 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 OH. Again, you look at this as Br anti, OH anti, Cl Markovnikov plus rearrangement. So 1, 2, 3, 4, boom, boom. And then with this, we're breaking the double bond and just going to have that's about as close as I came to writing 2, 1, 2, except for now this is an oxygen. That's all you have to do, and I think it was for them choose 2. This is when we had the 1,2-dimethyl, yeah? This adds syn, and it adds two OHs. So for this one, you just get OH, OH, and you have to show the full stereochemistry where one's a wedge, the methyls are both dashes, and you can say meso. For MCPBA, you're going to get the epoxide, and don't forget my methyls, and the methyls will be on a dash, and that's also meso. This is a generic peroxy acid. MCPBA is a specific peroxy acid. So again, initially I form the epoxide, then I open it to get, boom, and I get I'm going to say my methyl's a wedge, my OH is a dash, and here my OH is a wedge, and my methyl is a dash. For this one, last one, I add anti, and again, one methyl is a wedge. I'm just going to say my bromine is a dash, and I'm going to go up here just because I can, and then OCH3, and this methyl is a dash. Again, it's about showing that what adds and that correct stereo and regiochemistry. For these, that was not really relevant. Lindlar catalyst. Now we're just going to look at these. This had some Lindlar to it. So Lindlar, this is going to give me my cis alkene. So I'll start with my alkene. That's all I had to do. Trans alkene. That's that. This one, I would have taken either spot because there really is not a Markovnikov anti-Markovnikov. Technically, this is the less sterically hindered, so this should be the spot you add to. So that would be, boom, boom. I hate this. Okay. Here's my double bond O. Boom. This carbon, and then these two. That is technically what it would be. This one, again, I would take either the one above or this one. Okay. Br2 one equivalent. I'm still going to have a double bond. And my bromines will be trans. Here I'll still have this. And here I'll still have my ethyl group. And here I'm going to add HCl. And again, it will add to one of these two, and whichever one it adds to, it will add a second time to. I would have taken either spot on your answer because I did not use a terminal alkene. 3, and I'm going to add 2 chlorines here, Cl, Cl, boom, boom. There you go. And then for the ozonolysis, you just break that, and you should have, I'll write it over here, the 2 carboxy acids. OH. There's that. And then there's 1, 2, 3. CO2H. And that would be that answer. And then I will ignore this key. I'm going to have to, because it doesn't go to this. So when we look at our one-step synthesis, if we look, there's a couple different ways to do this. Probably the most straightforward for this first one is to just start with an alkyne, 2, 3, Cl, and then this would be here, CH3, and you could use either H2/Lindlar or NH3. Either one would work. That I would take if you did this and you used HCl with peroxides, because we didn't go over that. But this is technically probably the better way to do it. For this one, to add our chlorine here, specifically, we would probably need to do a substitution. So you could do something like, and again, there are multiple ways. I cannot show you every answer that could be correct because there's multiple ways to do it. Something here and HCl. Here again, for number 3, this is clearly an alkyne addition. 1, 2, 3 with HCl. Now for this one, if you wanted to do, again, multiple different ways, you could do an SN2 here to get that chlorine, or you could do an elimination, an E1 elimination to get this double bond. If you're doing an elimination, so if you're doing an SN2, it would be similar to what I did in question number 2. E1, and again, anytime you're looking at a one-step synthesis, just start with what you had. 2, 3, whoops, 2, and then 3, 2, 3, and here we go, 1, 2, 1, 2. And all I'm going to do is I'm going to put a leaving group here like OTS. And I'm going to add heat. And I'm just going to say ethanol. You could even say, you could say whatever you wanted. You could have bicarbonate if you want to use a weak base, whatever. So that's this one. To be able to form this double bond, this could either be E1 or E2. If it's E2, you could start with something like 1, 2, 3, 4, 5, 6. And here's this methyl. I could, if I wanted to, just have my leaving group here. And then just say NaOH. And heat. I could also put my leaving group in here and use a bulky base. Either will work. For this question here, again, I could use HCl and a double bond, or I could do an SN1 reaction, but usually alkene reactions yield less diversity in product, so I would just do something like a double bond here, and HCl. For this last one, this tells me that I had an alkyne. So probably the easiest way for me to do this is I could do either of two things. I can have my alkyne, and I can have then CH2, CH2, 1, 2, 3, 4, CH2, CH3, and then this forms this plus CO2, or I could, on the other side, have the exact same thing. We have CH2, 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 CH3, and both of these would yield that product. Okay, that's my key. Keep in mind some of the things, there may have been additional ways, especially on this page, to do it that would also be correct. So I showed you the ones that come quickest to my mind right now, but take time, think through your problems. Thank you.